This is video 2.6.3, and the goal in this video is to be able to solve real-life problems using rational functions and their graphs. So everything we've learned about their graphs and what happens as x gets really large and which direction do we point our graphs and so on is going to help us solve these real problems. So first of all, there's one real-life problem that's often described by a rational function, and that's understanding the cost and average cost functions. So a simple way to understand the cost of a business is to think about adding two different costs. Number one is fixed cost plus the variable cost. So a fixed cost, for example, is something like if you were trying to open up a restaurant. A fixed cost would be the cost of all the plates and glasses, the cost of the building, the cost of the tables to eat at, the cost of the grills to work at, and then the cost of the waiters, so every day you'd have this many waiters, and that's a fixed cost. What's variable is the cost that you'd pay for the meal, okay? So you have a cost for the meal. So the meal itself costs only $10 for every meal to create that salmon 3-course dinner for the restaurant. So that's a variable cost depending on how many you sell. Okay, same thing for like t-shirts. If you were trying to sell t-shirts, fixed cost would be the cost for the screen printing, the machine to do the screen printing. A variable cost would be the cost, okay, every time you make a t-shirt, it costs you money because you got to pay for the t-shirt and you got to pay for the actual printing. So that would be a variable cost. That depends on the number that you produce. So the average cost is a little different than actually just calculating the cost, but of course average is just adding everything up and dividing by the number that you sold. Okay, so this down here describes the average cost. So we take the cost of producing X items, okay, X items, so we take the fixed cost, which is some dollar amount, plus the variable cost per X, and then divide it by the number we produced, which is X. And this is a rational function, okay, with X as the denominator. It's a rational function. And hopefully you know from past experience of understanding this that there's definitely going to be some money that you have to put out, but over time the average cost should go down, right? Because over time you should have that fixed cost split between more items. So let's take a look at this in action. So we're looking at the Fort Myers Fishing Company. They discovered a better material for making fishing reels. The fixed monthly cost is $10,000 for the cost of rental space, manufacturing equipment, as well as wages and benefits for its employees. So no matter what, they're going to pay 10 employees, they're going to buy all the equipment and rent the space. So $10,000 is their fixed cost. It costs $10 for materials to make each fishing reel. So write a cost function C of producing X fishing poles. So based on their function over here that we see that for question A, the cost function is the fixed cost, so $10,000 plus 10 times the number that I produced, X. The average cost, which is what question 2 is asking, average meaning C with the bar over it. Hopefully some of you have seen that in your statistics courses. The average cost is taking that cost and dividing by the number of items that we actually produce. So the cost function divided by X. Now they want us to find and interpret. So when they say interpret, we're looking for, okay, what does that mean? What does that number mean? So they're telling us find C bar of a number. In this case, the number is 1,000. Well, we know that means plug in 1,000. So we're going to plug in 1,000. Then we're going to divide by 1,000. And we're going to see what value we get. So in calculating this, we're going to get 20. So we get a value of 20 here. So what does that mean? That means that when X is 1,000, and let's go back to the problem, X represents the number of fishing poles. So when we produce 1,000 fishing poles, then the cost will be $20. The average cost per pole, right? $20 per pole. Okay, so $20 per pole, that's not too bad. Okay, we'd probably have to sell them a little bit higher so we can make a profit, but if we make 1,000 fishing poles, then the cost would be $20 per pole. The next question, though, says, what about 100,000? So the next one's asking us, tell us the average cost for 1,000 items. So now we're going to plug in 1,000. So let's plug in, 100,000. So we're plugging in 100,000 for our x. So 100,000 in for our x. And we'll see what our average cost is now. Our average cost in this case is going to be $10.10. So wow, our average cost for 100,000 fishing poles is only $10. So it would be worth our while to produce 100,000 fishing poles if we can sell them. So what does that mean? That's the interpretation. We interpret it by not just giving a number, an answer like you see here, but we make a sentence and we say, if we produce 100,000 fishing poles, then the average cost is $10.10. Okay, that is the statement we would answer for interpreting the cost. So what about the final question? What is the horizontal asymptote for the graph of the average cost? Describe what this represents for the company. So let's look back at the average cost function. Looking back at the average cost, so we'll forget about all this stuff. Looking back at the average cost function that we see here, we want to look at the horizontal asymptote. Well, we know horizontal asymptotes, we look at the degree of the numerator and denominator, and they're both of the same degree. They're both x to the first. So remember, what that means is we take the ratio of the coefficients. In this case, 10/1. And we see the ratio of the coefficients is 10. $10 in this case, because we're looking at the bound on y. So that means there's a horizontal bound where y equals 10. And y represents money. So what does this mean for the company? This means that the company could never have a cost smaller than $10. Couldn't even have a cost equal to $10. They'll get infinitely close to $10, but they'll never be equal. Remember the two values that we just found. We just found two values that at 1,000, the company would have a charge of 20 for the average, but at 100,000, which is way out here, they'd be at 10.1. So we have a graph that looks like this. Okay, we have a graph that looks like this. It's going to be a curve. Hopefully it's a curve better than mine, mind you. It's going to be a curve like this. It's going to get infinitely close to $10, but it'll never be less than 10. So that's what we would analyze for the company. You'll never be able to sell the products for less than $10. It'll always cost you $10 to make these products, $10 or more. So that's one of the examples you'll try in your checkpoint and in your classwork on Friday. Let's take a look at 92. So in this case, they gave us the function, but we want to make sure we understand what it means. This is question 92 in your book. So a drug is injected into a patient and the concentration of the drug is monitored. The drug's concentration in milligrams per liter after T hours is modeled by. So let's see, C is the concentration. That's how much stuff is in your blood. T is the number of hours. Okay? Here's a graph of this function. Notice that right away it spikes and then it starts to fall. That should make sense. If you take Advil, it's going to spike right away. If you take an antibiotic, it's going to spike right away. And then it'll trickle out of your body. Now let's look at the questions that follow this problem. Use the graph to obtain a reasonable estimate of the drug's concentration after 3 hours. So let's see, 3 hours, understanding the scale of the graph, x goes from 0 to 10, and every mark is 1. So there's 1, 2, 3. Looks like at 3 hours, we're right about here. So we're going to go over to y. And y is also going by ones, and it goes up to 3. So that's 1, 2, 3. And it looks like it's at about 1.4 perhaps. So I'm estimating that the drug's concentration will be about 1.4 milligrams per liter. I'm going to verify it algebraically by simply plugging in 3. So for question A, I'm going to verify by plugging in 3. 5 times 3 over 3 squared plus 1. Use the function they gave me to plug in and find the value. 15 over 9, which is 1.6 repeating. So my estimate was a little off. Probably good I verified it algebraically. It looks like 1.6 milligrams per liter are still in your body. Okay, or 1 2/3. Question B. Using the function, find the horizontal asymptote for the graph. Describe what this means about the drug's concentration in the patient's bloodstream. Horizontal. So we can see that there might be like a bound here. We can kind of see that this graph doesn't quite seem to be bordering 0. It seems to be bordering something else. So let's take a look at what that bound is. And remember, we look at the function 5t over t squared plus 1 to see what that bound is. But it looks like there will be a horizontal asymptote. This has a degree of 1, and this has a degree of 2. So that means that there will be a horizontal asymptote at 0. Whenever the top, the numerator, has a smaller degree than the denominator, it looks like it will go to 0. So while our graph doesn't show us that, it must take quite a long time to do that, but it actually is going to go closer and closer and closer and closer and closer to 0 based on what we know about horizontal asymptotes. So my horizontal asymptote is 0, and what that means is that eventually the patient's bloodstream will pretty much get rid of the drug. Will it ever be exactly 0? No, it will never be exactly 0. There will always be a trace amount of that drug in that patient's bloodstream, but it might get so minuscule that we cannot measure it. So there will eventually be a tiny bit of the drug, very little, so much that we can't even describe it. Your checkpoint for this particular video is to try question number 90 in your textbook. So I have the question here, for those of you that do not have a textbook, but it is question 90, and it's similar to the first example you saw in this video. So give it a shot, bring in your questions, we'll go over them in class.